welcome everybody. So this is the first FLOW seminar of 2023. So for those of you attending for the first time, FLOW stands for Federated Learning One World Seminar. I was created to provide a global online forum for the dissemination of latest scientific research in all aspects of federated learning. And this includes, but not limited to, distributed optimization, learning algorithms, privacy, cryptographical techniques, personalization, and many more. So today it's my great pleasure to introduce our speaker, Gauri Joshi, who is an associate professor at the ECE department at Carnegie Mellon University. So she, in her research, she mainly focuses on designing scalable algorithms for distributed machine learning and large-scale parallel computing. And yeah, so she works a lot on federated and distributed learning, many interesting work that you should check out, and including the one or few that she's going to discuss today. And her talk is titled Leveraging Spatial and Temporal Correlations in Distributed Learning. So thank you, Gauri, for agreeing to giving a talk, and looking forward to it.
Thank you very much, Samuel, for the invitation and for the great introduction. So today I'm going to present some joint work with several students and collaborators listed here, but mostly led by my PhD student, Divyansh Junjunwala. It is based on two papers that are listed here. You should be able to find them online later on in case you're interested to read more. So this work is on leveraging spatial and temporal correlations, as the title suggests, and one of the applications is federated learning, but there are also other applications in aggregation of data from a distributed system of nodes. So the applications are a little broader than federated learning. So since this is the FLOW seminar, and I assume everybody already knows federated learning, I'll not spend too much time introducing and motivating it, only a couple of slides for those who might be new to the topic, and then I'll just directly go to the main topic of the talk. So as I mentioned, one of the motivations and the applications of this work is federated learning. And the reason why federated learning is becoming so popular in the past few years is that in many modern applications, there is massive amounts of informative training data that is collected by edge devices like cell phones, tablets, etc. And these devices, if they want to use standard machine learning training to obtain a model, they would have to send the raw data to the cloud for the purpose of centralized training in the cloud. But that can be too expensive and slow when you have large data to communicate and a large number of resource-limited and bandwidth-limited devices. And moreover, there can also be privacy laws that forbid data sharing across geographic boundaries and across time zones. Federated learning is a new field that tries to operate within these communication constraints and privacy constraints and still train informative machine learning models. So the main idea of federated learning is that you keep the training data at the edge device. You don't have the edge device send all the training data to the cloud, and instead we shift model training to the edge. So the main idea is that each edge client will perform a few steps of local training using stochastic gradient descent, and then the resulting models are aggregated by the central server. So by keeping the data at the device, we get better communication efficiency and also better privacy guarantees than sending all the data to the cloud. So that's the core idea. Now let me quickly define the notation that I'm going to use in this talk, and then start off with the main topic of leveraging spatial and temporal correlations. So in federated learning, now since the data is collected by each edge device separately and independently, each device will have a different local data set which may be heterogeneous both in terms of the size and the distribution of data. So each device has a local objective function, which we denote by Fi of x. X is the model parameters or the parameters of the, say, the neural network that we are trying to train or any other machine learning model. And Fi of x is the empirical risk objective function computed using the data di that is stored at this ith edge device. So we have n edge devices in total in the system. And our goal is to minimize a global objective, which is the weighted sum of these local objective functions. And the global objective is defined as shown here, which is a weighted average of the local objective functions. And this weight pi is typically set to be the fraction of data at the ith device. And the reason for this is that we want to emulate centralized training, where hypothetically, if all these edge devices had sent their data to the cloud, then this would be the weight that is assigned to the ith edge device. So there are variants of this objective function where you can set the weights pi differently to meet fairness, privacy, and other constraints. And there are also variants where you don't necessarily want to train a single model X, but rather several personalized models that could work well for different clients. But for simplicity, right now, let us assume that we only want to learn a single global model that minimizes this objective function. Right, so that is the setting in terms of the objective functions. Now let us see the algorithm. What is the standard algorithm that is used in order to minimize this objective function? The standard algorithm is called FedAvging. And the core idea again is that you don't share data to the server, keep the data on the device. So to operate within that constraint, the algorithm proceeds as follows. In every iteration, these edge devices, they will read the current version of the model from the cloud server. Then they will perform tau local steps of SGD on their local data. And then these updated local models, which can be different at different nodes because of the data heterogeneity, they are aggregated by the central server in proportion of pi, which is the weight assigned to the ith client. So this is the algorithm, and the algorithm just proceeds in these communication rounds of tau local updates each. So as you can see, a core step in this algorithm is the averaging or the aggregation of these locally trained models. So effectively, what we are doing is we are estimating the mean of these models that are obtained after local training. So in this talk, I'm going to focus on this problem of mean estimation. So abstract out the other details and try to focus on the fact that you have these different nodes. Each node is sending some vector, which in the case of federated learning corresponds to the model update or the gradient that is computed locally. And then the central server, with a system of these capital N nodes, it seeks to compute the mean of these vectors. So let us consider D as the dimension of each vector, and these vectors are sent to the central server at the same time, and then the central server computes the mean X bar as shown here in the picture. So besides federated learning, this scenario where you need to estimate the mean of several vectors arises in different applications. It could be like a sensor network application where you're aggregating information collected by different sensors, or also algorithms like distributed k-means clustering or power iteration, etc. Right. So now let us think about this problem of distributed mean estimation and understand what are the constraints that would arise in a practical setting to achieve this mean estimation and achieve a perfect estimate X bar. So in most of the applications of interest that I described, these client devices are resource constrained and bandwidth constrained. And the vectors that we are talking about here, which have dimension d, are becoming larger and larger as the models are getting bigger, the machine learning models that we are training. So sending high dimensional vectors to a central server may not be possible for these bandwidth limited nodes because of communication constraints on this link. So when you have bandwidth limited clients, sending such high dimensional vectors is expensive. And a solution that is employed in practice is to compress the vector at each node before sending it to the server. And this compression can be achieved either through quantization or sparsification or a combination of both of these or any other techniques that are existing in the literature. So for example, if you consider quantization, in quantization, each element of or each coordinate of this vector is represented by a fewer number of bits. So that is one way to reduce the total number of bits that we are communicating. But the downside is that it won't reduce the dimension of the vector itself. It will only reduce the number of bits used to represent each element. On the other hand, if we use sparsification, we only retain a small number of coordinates of each vector, and we only send those retained coordinates and their locations to the central server from each node, and all the other coordinates that are not sent are assumed to be 0. So sparsification is especially suited for machine learning applications where the model parameters and gradients are naturally sparse. A lot of the elements are 0 or close to 0. And overall, it would require far less number of bits than the uncompressed original vector. So for this talk, I'm going to focus on sparsification as a method of compressing these vectors, but in general, it could be combined with quantization techniques as well. So sparsification is a way of reducing communication by just retaining few number of elements, and the adverse effect of sparsification would be that when you estimate the mean of these vectors, there will be some error because now we don't have information about these elements which are set to 0. So that's one communication constraint and how we address it. Another communication constraint that is prevalent in these systems is that you have a large number of nodes here. So in federated learning, there can be, say, thousands of clients. And these are only intermittently available. So at a given time, only a small subset of them are available. And this is because in current applications such as, say, next word prediction on Android phones, the cell phones are available for training only when they are plugged in for charging. And since users mostly charge their phones at night, the availability of these devices can vary across time zones and locations. So ideally, we wanted to compute the mean of all of these vectors, but now if some clients are not available, like the ones shown in gray here, what do we do? So the solution is that we can just compute the mean of the vectors that were sent by the participating clients and use this partial mean as a proxy for the true mean that we would have computed if all the clients had sent their vectors. So the goal of this talk is to understand how Sparsified communication and intermittent client participation can increase the mean estimation error because you're losing some information in both of these techniques. And then how do we reduce that error? The way we want to reduce that error is by leveraging spatial correlations between the vectors sent by different clients in one iteration of the algorithm, as well as temporal correlations between the vectors sent by the nodes at different iterations of the algorithm. So first, I'm going to talk about just sparsified communication, and then talk about how to consider spatial correlations in this context, and then temporal correlations. And then in the last part of my talk, I'll go to intermittent client participation and show how we can leverage such correlations in that setting as well. So let's start by talking about spatial similarity. So why do we think there will be spatial similarity across the vectors sent by different nodes? So there can be several reasons for this. One of the reasons is that the nodes which are in similar or same geographic locations will tend to have similar local data and then send vectors that are correlated with each other. Secondly, when we perform an algorithm like local update SGD in federated training, all the participating nodes in a given communication round, they will start off with the same global model. And then if the local learning rate is small enough, then the model does not change much in one communication round. And as a result, the updated models will not differ that much from each other when you look at different nodes. So because of that also, there can be spatial correlations, not just in between clients that are in the same location, but also clients that are across locations. So let us see how we can leverage such spatial similarity to reduce the error in sparsified mean estimation. So we are going to focus on a simple sparsification technique, which is Rand-k sparsification, where if you have a system of n clients where each client is sending a d-dimensional vector, the way they sparsify it is that they take the vector and they retain only k out of d randomly chosen coordinates of that vector, and the remaining are just assumed to be 0. And this sparsified vector is denoted by hi, as shown in this picture. So the white dots represent elements that are set to 0, and the colored dots represent retained elements of that vector. So now each client will sparsify its xi to the vector hi and send these hi vectors to the central server. And then the central server will compute an average of these sparsified vectors in order to find the mean of them, find the mean estimate, which is denoted by x hat here. So one thing to note in the mean estimate is that x hat is not just equal to the average of the sparsified vectors, but it is also scaled up by this factor d over k. And the reason for that is that we want the mean estimate to be unbiased. And in order to compensate for the fact that we dropped some coordinates of these vectors, assumed them to be 0, we need to multiply the mean by this factor d over k in order to make sure that it is unbiased. So now if we compute the MSE, or the mean square error of this estimated mean, it's given by this expression. This is well studied in existing literature. And if you look at this expression, there is a summation over the norm squares of the vectors here. And then there is this multiplicative term, which is proportional to d over k. So d over k is how much you're sparsifying each vector. So the more you sparsify, the higher this error will be. Now, let us think about, can we reduce or eliminate this factor d over k if we knew that these vectors were similar to each other? So to understand how we could potentially do that, the question that we want to ask is, can we reduce this factor of d over k or even eliminate it by being smarter about what these vectors are? If we knew that they were correlated, we could do much better. So let me illustrate that with a simple toy example. So let's consider that you only have 3 nodes and each of them is sending the same length 3 vector. So now these vectors are all identical. And then if they sparsified these vectors to just retain one out of those 3 elements, if we used simple Rand-k sparsified mean estimation at the server, then to compute the first element of the mean, you would do something like this. So you take an average of these coordinates that were sent by all the nodes, including the 0, and then scale it up by a factor of 3 to make it unbiased. So observe that this does not recover the true mean. And the main reason is that we have the 0 and we are still giving the same weight to that. Now, instead, if we know that these vectors are identical or mostly similar, can we design a better estimator? So a better estimator, which is in fact optimal when there is full correlation between these vectors, is that we should only take an average of the non-zero elements at that coordinate. So you only consider clients who retain that coordinate and ignore the clients who have set that coordinate to 0. So if we do that, then we would get this coordinate as x1, which is the true mean. And we could get that similarly for all the other coordinates. So what this example illustrates is that we should be more careful when averaging over 0 elements or these sparsified elements of the vectors. So here, this was an extreme case where there is full correlation, but can we modify this strategy where there's arbitrary spatial correlation between the vectors? So let me first define what I mean by spatial similarity or correlation. If you're given a system of n nodes, then let us define R1 as the sum of the squared L2 norms of these vectors, and R2 as the sum of the inner products of different pairs of the vectors. Then we define spatial correlation as R2 by R1. So this is a way to measure spatial similarity. It's not the only way. There can be other ways to measure similarity, but this is what we consider. And observe that this parameter rho that we define lies between -1 and n-1, where n is the total number of nodes in the system. And if all the vectors are identical, then rho is equal to n-1. If they are orthogonal to each other, rho is equal to 0. And for other values, rho will take some value in between -1 and n-1. So now, based on this definition, what we do is that we define a family of estimators, which is parameterized by a vector W. So what is this W? The W is dependent on the number of clients that send that particular coordinate of the vector. So what we define that the jth coordinate of the mean is proportional to the sum of the HIJs, the sparsified values, divided by WM, where WM is the mth coordinate of this vector W, and capital M is the number of nodes that sent the jth coordinate and did not sparsify it to 0. So this family of estimators subsumes several existing estimators. For example, the Rand-k estimator is a special case of this family where we just set W as equal to 1, 1, 1. It's a vector of all ones. So what this means is that when we divide the sum of HIs, we do not take into account the fact that, say, only 2 nodes send this coordinate versus 1 node send this coordinate, or all the nodes send that coordinate. And another thing to observe is that this is a proportionality sign here. So there is also a scaling factor that we need to compute in order to make this unbiased. And that scaling factor for the Rand-k estimator is this. So another special case, which we showed in the previous slides example, is when you consider the full correlation case, where you only average the elements across clients that actually send them. So here, this W vector will be 1 to n instead of being all ones, and the scaling factor would be this. So what we are doing here is that by making different choices of this scaling or normalization vector W, we are getting different estimators. So how do you choose this W in practice? So what we can do is we can actually express the mean square error of this family of estimators parameterized by W and the correlation factor rho that I defined earlier. And this is the expression that we get. So observe that this expression is very similar to the mean square error of the Rand-k specified estimation, except that you have this additional GW rho term. And since this is negative, if we maximize this term for a given rho, then we can minimize the mean square error. And it turns out that this can be maximized by setting the W vector in the following way. So the mth element of the W vector is chosen as this, which is a function of rho, the spatial correlation. So now what we have here is that if we knew the spatial correlation rho, then we know what is the optimal estimator that will minimize the mean square error, and that is given by just setting this W vector as this. And there are several special cases for different values of rho. So if this rho was 0, there was no correlation, then we get back our Rand-k sparsified mean estimation. If the rho was full correlation, that is n-1, then you get W star m equal to m, which was that optimal estimator that I showed in the toy example. And then if rho was somewhere in between, then we would get W star m equal to 0. So this just tells us what should be that scaling factor in the denominator. And let me show you some simulation results which show the MSE versus rho. So this flat line corresponds to Rand-k because it just does not consider rho at all. When setting Wm, it's just set to 1. And what we see is that for high values of rho, we can significantly improve on this MSE of Rand-k by using one of these other estimators like the max or the average, etc. So the orange line here shows the optimal estimator. If we exactly knew what rho is, then we would always choose W star by this as given here and get this minimum possible error. So that gives us a lower bound on the error that we can achieve. And then the flat line, the blue line, shows the worst case error. If we did not know anything about a rho, this is the worst case error that we get. And by assuming rho as something else, which may not be true in practice, we can get these lines, which are the blue, the assuming maximum correlation, and red, which assumes some average correlation between the vectors. So the key takeaway here is that if we guess the correlation as something, we can set the estimator accordingly. And if our guess of rho is close to what is the actual rho, then we get a really good estimator. So another viewpoint of this is that what is the min-max optimal estimator? So since our guess of rho can be really bad, what is the worst case estimator that we get? So it turns out that the Rand-k spatial original estimator is actually min-max optimal. And then if you consider, say, a uniform prior on the actual rho, then the Bayes optimal estimator is this Rand-k spatial average, where we assume that rho is equal to n divided by 2. So that was about how to leverage spatial correlation. So the key takeaway here is that in many practical applications, Rand-k estimation is too conservative because it assumes that there is no correlation between the vectors. However, if we actually measure this correlation for different data sets, then we can see that the value of rho can be pretty high. If we leverage that, then we can do much better when we estimate the mean. So considering a uniform prior on rho captures many real-world scenarios well, and then we can use this Rand-k spatial average estimator, which sets rho equal to n over 2 in many cases successfully. And more generally, we can consider some prior distribution on rho and then compute rho hat accordingly in order to choose one of this family of estimators. So that was the first part of my talk. I can pause and take questions. The second and the third part are not very long, so I think I'll have time to finish.
Right, so please, if you have any questions, just post it to the chat or just raise your hand and I'll try to unmute you. So yeah, I would have actually two questions. So starting on your motivation, like there you described that like essentially like if all the vectors are same and then you apply like Rand-k, so if two clients sample the same value, then you should just average those two and ignore zeros. But do you think that you can actually, like, if you assume that the correlation is very high, that maybe you want to kind of adapt the Rand-k itself such that like there are no like so if you have, like, let's say, like you have number of clients to be equal to the dimensionality of your model, so essentially like each client sample just like each client sample different coordinate, and then you would have like an exact recovery.
Yeah, I think that's a good question. So what you're suggesting is like currently the way I showed it is we only change the procedure at the server. Each client still does Rand-k, but can we do better by, say, sampling coordinates more smartly? So that is actually an open direction which we did not address. So you could do something like top-k or other better compressors. And,
so there is a
or use I think like sketching techniques as well.
So there is a paper by Peter Itharic and his students that essentially like discuss that like this kind of a Rand-k like a permute k compressor, where essentially like every client sample different coordinate such that if the clients have very similar updates, then your mean is closer to the true update rather than just sampling uniformly at random in each client. So it might be I think a good thing to combine both.
Yeah. So actually later on, I have some results with some of those estimators that do smarter sampling than Rand-k, but I may not have covered the specific paper that you mentioned.
Yeah. And by the way, so here, is it also, here, I guess, like you kind of, your method as you presented is data agnostic, right? Or did I miss something?
Yes,
so
it
can
is
you
data
actually,
agnostic.
So can you actually benefit while like adjusting your estimate of rho while you running the algorithm? And is there essentially efficient way to estimate the correlation, for instance, like without breaking the privacy guarantees of federated learning?
Yeah, that is also a really good question. So as an algorithm proceeds over time, the row can change. So if we can estimate it, then we can use that in this procedure. So yeah, I mean, a naive way is to just estimate based on the last value of the sparsified vectors that were sent. But I mean, there could be smarter ways. We haven't looked into that.
Yeah, thank you.
Sure. Okay, so now let's talk about temporal correlations, how to leverage them. So I want to just mention that there is a lot of existing work on this already. So the method that we are going to propose is kind of similar to several of the existing works and gives similar performance and insights as them. So the idea of temporal correlations is simple, like if the client is sending vectors that are similar across consecutive communication rounds, can we leverage them, this knowledge to design a better mean estimator? So why do we do that? The main motivation is that something like Rand-k would estimate a mean of a coordinate as shown here, where it just assumes zeros as is. But we could do something better than just considering zeros here. So if we knew that this client had sent a different vector in the previous iteration and it had not sent zero, then maybe we can use that information instead of just substituting zero for these unsampled coordinates. So that's the key idea. And how do we do that? A simple way to achieve this is that the server can maintain in memory a vector bi for each client. And this bi is just initialized as zeros as shown here. And whenever a client sends a coordinate, you just update that in the server memory by filling in that corresponding value of bi. And we can keep doing this across iterations. And the advantage of this is that now this information that is stored in server memory can be used to fill in missing coordinates in future iterations. So a naive way to do that is that in any iteration, we can compute the mean, the jth coordinate of the mean, by just either taking the newly sent coordinates, if the client actually sent those. And if the client did not send a coordinate, you just use the value from memory, and then you can take an average of this. So this is an easy way to compute the mean. But there is a problem with this. If we just compute the mean in this naive way, then it is not unbiased. So it has some bias. And to see that, we can show that if we consider the expected value of this jth coordinate of the mean, it is not equal to the jth coordinate of the true mean. So how do you overcome this bias? To overcome this bias, we need to just define this xj hat in a slightly different way. So we need to define xj hat as shown here, where what you're effectively doing is taking a sum of all the elements stored in server memory, and then adding to that d over k times the sum of the differences between x and b for the clients that actually sent the jth coordinate. So in other words, what we are doing is we are considering a Rand-k sparsification of the vector xi minus bi as this first part, and then adding to that whatever is there in server memory in order to get this unbiased estimate of the mean of that coordinate. And we can show that the mean square error of this estimator is given as shown here, which looks similar to the Rand-k estimation expression, except that instead of xi, now we have xi minus bi. So as long as our bi, whatever is stored in memory, is a good guess of xi, such that xi minus bi is much smaller than xi itself, then we can get a much lower error in estimating the mean. So note that although I'm defining BI in a specific way here, where you fill in elements in server memory, there is quite a bit of flexibility here. BI can be chosen in other ways as well. So if you don't want to maintain one element, one vector in memory for each client, you could consider clusters of clients, or you could update BI in a lazy way only after a few communication rounds, etc. And then the rest of the procedure would still remain the same. And this would be the error that we would get with the Rand-k-Temporal estimate. So we ran some experiments for this for a simple quadratic objective where the algorithm is similar to Fedavg that I described earlier, where the current model is sent to the nodes, then they compute local gradients, and then these gradients are aggregated. And this is the result that we got when compared with Rand-k. So here, the Rand-k estimation gives the blue line, whereas the Rand-k-Temporal estimators, by leveraging this iteration-wise correlation, gives a much lower estimation error over time. And this is also true for other applications. So let me talk about now the distributed power iteration and k-means, etc. And in these simulation results, I'll show the performance of both Rand-k spatial as well as Rand-k-temporal, the two estimators that I defined. So here we are also comparing with some existing works that do the Rand-k sparsification in a smarter way. So instead of just retaining subset of the elements, they do something better, such as some like combining it with other techniques such as top K, etc. And one of the works is by Samuel. So in this plot, you can see that over time we are plotting the error in estimating the top eigenvalue of a data set. And the Rand-k spatial estimator gives a much lower error than Rand-k, and Rand-k-temporal estimator does better as the iterations progress. So potentially we could even combine these two strategies to get the best of both worlds if we knew how the correlations are changing over iterations. Similarly, for distributed k-means clustering, also we get a big improvement when we use either spatial or temporal estimators and a significantly lower error floor. One place where this method does not work that well, especially the Rand-k spatial one, is when the data is highly non-IID across the node. So we tried this for a logistic regression with a non-IID partitioning of data. And in that case, the Rand-k spatial did not do very well because there was not that much correlation between the vectors across the different nodes. So improving this method for non-IID data sets is something that is a part of future work. So wrapping up these first two parts of the talk, the key takeaways is that by leveraging spatial and temporal correlation, we can improve the mean estimation procedure. And the main advantage of the techniques that I described is that they don't use any extra computation or storage at the nodes. We are only modifying the server aggregation method. So these techniques could be combined with other previous works that modify the local computation at the nodes and they are kind of orthogonal to them. So future directions include adaptively combining these estimation methods, reducing the server storage cost, and then considering other sparsification techniques besides just Rand-k. So that was wrapping up the first part. Are there any questions? I'll take like 5 more minutes to finish the last few slides that I have.
Yeah, I don't see any questions here. Yeah, so
Okay,
I guess you can just continue.
Sounds good. So let me continue and you can ask me questions at the end. So far we only considered how to leverage these correlations when we are doing sparsified mean estimation. But at the beginning of the talk, I mentioned about intermittent node availability, where you have a partial set of clients who are participating. So it turns out you can also use correlations to overcome the added error that we have due to partial client participation. So here now let me go back to federated averaging. In federated averaging, if in every round, you only have a subset n out of the capital N clients participating, where the small n clients are chosen uniformly at random, then it has been already analyzed that the error that we get after T communication rounds is bounded as shown here. So the first 2 terms of this error are mainly coming from the stochastic noise in the local updates. This last term is coming from data heterogeneity across clients. So sigma G square here that I'm writing is a measure of data heterogeneity. And then this third term is the error that we get because only a subset of clients participate in this process. And it turns out that if you set the learning rate appropriately, this partial participation error is dominant. So you can see that it decays as 1 over square root of T, whereas client drift error just decays as order 1 over T. So how can we overcome this error? So one idea that we try to use in this work is that we try to mitigate it by using correlations in client updates across rounds. And we propose a method called FedAvg, which is similar to our Rand-k-Temporal thing that I showed before. But now what we are doing is we are trying to, instead of filling in missing elements of sparsified vectors, we are filling in for missing clients. So we again have a server memory, one for each client. And then whenever a client sends its update, we store it in the server memory. And then at the time when you don't have some clients updates because they are not participating in that round, you can use the value that is stored in server memory to fill in for the missing vectors. And again, we can compute this variance reduced update, which is unbiased, and then use it when updating the global model. So it's a similar idea, but just applied in a different context. And it turns out that, so it turns out that this can eliminate this partial participation error and thus significantly reduce the overall error in Fed averaging. Now, the downside of this method is that it requires one vector in memory for each client, which can be pretty large in terms of storage cost. But then we can also come up with a variant, which is called cluster FedAvg, which reduces the storage by only maintaining a single state per cluster of clients. And this clustered FedAvg does almost as well as the original method. So these figures show comparison of the FedAvg method with Fed averaging and also other methods that are previously proposed. So with that, I'm going to wrap up and conclude to say that although there are communication constraints which lead to an increased mean estimation error, we can leverage correlations to reduce that error. And future work includes extending these to more general compression schemes and also combining spatial and temporal techniques. So thank you, everyone. Let me know if you have any questions.
Thank you, Gauri, for a great talk. So just a reminder for everybody, if you have any questions, just please post it to the chat or just raise your hand and then I'll just unmute you. Okay, so we have a question from Manav. Let me try to unmute Manav. Yeah, please go ahead.
Hello, am I audible?
Yes.
Hi, Gauri. Thanks for the wonderful talk. I just had a question regarding the non-ID setting which you had presented.
Mm-hmm.
So was it found that the correlations was not helping very much due to the way in which the data had been distributed amongst the clients?
Yes, I believe that is the reason. So because the data was split across labels in that experiment, it was too different across clients and there was not much correlation. So
Right.
the technique that we propose will work if there is more correlation across nodes, right? Or you have to just guess the correlation to be close to 0 and then the estimator becomes similar to Rand-k spatial estimate, Rand-k estimation again.
Right. So the algorithm caters more to an IID setting in that manner.
Yeah, or even if it is non-IID, it shouldn't be, the data shouldn't be too different across the clients, which I believe is somewhat close to practice. In practice, you don't have these extreme cases of data heterogeneity. There's still some similarity, at least within groups of clients.
Right. Thank you for that answer. And another question I had was, do you have any results which show with the increase in the number of clients, how was the method performing?
Okay. So if you increase the number of clients, the performance of the method will depend on, again, like how the data is generated at those additional clients that you have. So if there is a similarity with the existing clients, then these methods will perform well. Or if there is a similarity across different iterations of the algorithm. So it really depends on how the data is there at those clients.
Right. Thank you so much for your answers.
Sure.
So maybe I would have okay, there is a question from Anil. Let me try to unmute Anil. Yes, so please go ahead, Anil. Okay, so it seems I didn't manage to unmute Anil, but I can read out loud the question. So Anil asked, okay.
I see.
He's asking him, oh, this is the question. So how can we use federated learning for time series data?
Yeah, I see the question in the chat. So I think this is a more general question on federated learning itself. So I believe what you're asking is, what if this data is not static? What if it changes over time? How do you use federated learning over there? So this is also an ongoing line of research where we want to consider something like data drift or concept drift over time to improve federated learning algorithms. And I think that's kind of orthogonal to the talk, but it's a interesting line of work that is being studied recently.
So let me see if, yeah, maybe I would have one last quick question. So for this, for the updates, for these BIs, how do you estimate them? So do you essentially, when the new update comes, just set it to that new update? Like the new coordinate comes, okay.
Yes,
and do you,
so whenever a client sends a coordinate, you just fill it in memory.
Because I guess there would like to kind of have a bounded staleness, that maybe like there you want to have like a bit of a like dependence across the random case for given client, that essentially it's more like a random permutation, such that you have the coordinates kind of fresh, right?
Ah,
but
okay. Yeah, I think so. What you said about staleness is an important thing. So in the case of random sparsification, because you choose the coordinates uniformly at random, that staleness is controlled.
Okay.
So it doesn't affect the convergence, but if the coordinates are not sampled in uniformly at random, then you will need some other way to control the staleness.
All right, yeah. I guess, yeah, that's it for today. Thank you a lot, Gauri. It was really a pleasure to have you.